Hope my screen is visible. Okay, so we are going to start the new module or new chapter that is called process synchronization, right? So basically in a multitasking or multi-programming system, we have a multiple process competing for a CPU or a shared data or shared resources, right? So due to their execution criteria, the output value will be changed. Okay, so we have to synchronize those processes which are competing for the shared data and resources. Basically we are going to study about that things. So we will start from the simple definition. So process synchronization is a task of coordinating the execution of processes in a way that no two processes can have access to the same shared data and resources. Okay, so what is the meaning that? Let us suppose I have a two process P0 P1 and one shared data variable called data1, right? So P0 is competing for data1 or P1 is using shared variable data1 and P1 is also use this shared data variable. So you can say that data1 is a global variable for the both processes P0 and P1, right? So let us suppose this initially this value of data1 is 5. Okay, so P1 wants to change this to 4 and P0 wants to change this to 4 and P1 wants to change this value to 3, right? Means P0 will decrease by 1 and P1 wants to decrease by 2. Okay, so there must be a ordered execution. Means if both try at the same time, so what will happen? Initially we have a 5, P0 wants to 4 and P1 wants to 3. Okay, so it is not possible to execute at the same time, right? So either P0 will be execute first. Let us suppose case 1. What will happen if P0 execute? So it will be changed by data1 value by 1. And case 2, if P1 execute first, right? P0 execute first, then P1 will execute. Value will be what? 4 to minus 2, 2. If P1 will execute first, then value will be changes data1 5 to 3 and then P0 execute. So data1 value is 2, right? So here you can see that at last the value of data 1 is 2. Okay, so we are going to see in the next coming classes that these operations are not atomic. Atomic means we cannot change directly to the value decrease by 2 or 1. Okay, we have a micro instruction, okay, which have to execute, but during those micro instruction or execution of micro instruction there may be chances that context switching occurs. Okay, so there might be possibility that the execution of such codes are not possible in a atomic manner. So what is the atomic manner, we can going to see after some time. So basically what I want to say that it is a task of coordinating the execution of process so that at the same time shared data or shared resources will be not used by more than one process, right? Now what are the types of process? There are various types of process based on the different criteria, but we are talking here based on synchronization, right? So basically we have a two type of process. One is called independent, another is called cooperative, right? So independent process are those process which are not dependent on other process, or basically you can say that there are no data and resources are shared, whereas cooperating process are those process which are using shared data or shared resources, or you can say that one process affecting the other process, right? So you can write down independent process are those process, so the execution of one processes does not affect the execution of other process, right? Clear? So what I am saying that let us suppose there is a two process pi and pj. Okay, if there is no dependency on pi or pj, then we can say that these are the independent process. Means p1 will be execute its own, pj will be execute its own without affecting each other, right? Now comes on cooperative process. So a process that can affect or be affected, both the cases, that can affect or be affected by other processes executing in the system, right? So what I am saying, let us suppose there is a two process pi and pj. So you can see here pi affecting pj. If I draw a line from pj to pi, it means p2 affecting pi, right? So this is called cooperative process. Or let us suppose we have a two process Pi and Pj both are using shared data, then we can say that Pi and Pj are cooperative process, right? Now question arises here, why do we need a process synchronization? So why do we need a process synchronization, right? So we are going to see after some time that if we not synchronize the process, or in case of independent process it's okay, but in case of cooperating process or cooperative process, if we do not synchronize them, then there may be issue of data integrity or data loss or inconsistent data. So you can write first point is due to data consistency, okay, we need a synchronization. Next we have a race condition. What is the meaning of race condition? For time being I will just tell you in one line. Race condition means there is a shared data, right? The two process or multiple process want to change the value of that data, okay? So maybe chances that if order of execution of process will be changes, the value of data will be changed. Just like here you can see that in case 1, case 2, at last we have the same value, but when we go in the micro instruction level, which we are going to after some time, okay, so the order of execution matters and value will be not the same. Just like here data 1 is 2 and data 1 is 2 in both the cases, okay, so that is called race condition. That means the order of execution will change the value of shared data. So we need a synchronizer therefore to prevent race condition. Then next we have a deadlock prevention. So what is a deadlock? Let us suppose consider a railway track. Right. So let us suppose train A is coming from this side and train B is coming from this side, right? So what will happen when they reach at some minimum distance, okay, so both will stop, okay, so train A will wait for a train B so that train B will leave the track, and train B will wait for the train A to leave the track, okay, so both are waiting for the common resources. What is the common resources here? Common resources, that is track, okay, so you can see here A and B both sharing the common resources track, and A is waiting to clear the track and B is also waiting to clear the track, okay, so here what happened, there is no progress, so that is called a deadlock situation, right? So synchronization prevent the deadlock. Then we have a priority control. By use of synchronization, if process P1 wants to execute first, then P2 executes second, then we can control the priority using the synchronization algorithm. So priority control is the another reason why we need a process synchronization, right? Similarly, we have a concurrency control. Means let us suppose for the multiple concurrent process are there, how they can behave or how they can say execute the shared data, share resources, we can control using the process synchronization, right? And we have a management of critical section. So what is critical section? So the shared resources and shared data kept in a section, okay, so that is called a critical section, basically kept in a program uh, program or code, okay, with a separate section, so that is called critical section. So management of that critical section also falls under the process synchronization and many more, okay. So these are the basically important requirements for which we need a process synchronization. So let us see with some simple examples. So the first example is very simple, so I am writing this as a simple example. Let us suppose we have three processes. Process A, process B, and process C. And considering all these three processes are the cooperative process, means they have some common shared data or shared resources. So in this case, I am considering that I have a shared variable that is called data, right? So process A wants to change the value of data. So basically process A wants to write the write on data variable, okay, whereas process B and process C are only perform the read operation on the common data, okay. So if I can writing process A changing the data in a memory location, while other processes B and C are trying to read data from the same memory location, okay. So what will happen, let us suppose the value of data is what, 4 initially. Now process B and process C read this data, yani they can have the value of data is 4, data equals to 4 for B and C, but at the same time the process A change the value of data 4 to 5. So you can see that the value of or reading of the data is now inconsistent for the process B and C. So basically this is called race condition. So how we can prevent this from the race condition, or from the for timing leave the race condition term, you just use the inconsistent, right? Means the actual value of data is 5 but B and C read that 4. So it is called data inconsistency. How can we make sure that both the process B and C, okay, will read the correct value or a consistent value of data? We use the process synchronization. Means we make sure that only one process can modify or can read or can access the shared data at a time. तो अब आप बताओ, अगर ये डेटा का वैल्यू जब ये मॉडिफाई हो रहा था, अगर उस टाइम पे ये रीड ऑपरेशन को अलाउ ही नहीं करता, मींस प्रोसेस बी और प्रोसेस सी को ये एक्सेस ही नहीं देता, तो क्या होता? तो वो 5 हो जाता, तब फिर ये एक्सेस लेता, तो क्या होता? 5 ही लेता. तो दैट इज consistent due to synchronization. So only we have to focus one line statement for the whole module or whole chapter, that at any time for the shared data only one process can access it. Clear? Okay, let us move to the second example. Example 2, or you can say that this is our also motivating scenario. For a race condition in a single core processor. I am not discussing about the multiple core or multiple process. So in a single core processor. So this is very important, single core. So please mute yourself. So let us suppose I have two process 1 and process 2 having a common shared variable counter, that is a integer type. So I am writing some section of code of process 0, and then process 1, so there is some line of codes, I am not interested on that. The process 0 increase the value of shared variable counter, that is initially 5. Let us suppose this is integer type. Okay, so if process 0 increase the value by 1, so we can write counter plus plus, and there is some other line of code or section of code. Of course we are not interested on that. Then similarly process 1 decrease the counter value by 1. So similar code I can write, but instead of counter plus plus I decrease the value by 1, and then right. So these are the codes for the process 0 and process 1. Now I break this line of codes into micro instruction. Okay, so focus on counter plus plus and counter minus minus. Micro instruction. So when we go for the counter plus plus, so there is a ALU operation, right? Arithmetic logic unit operation. Similarly for counter minus minus, we have a again ALU operation. Now how this ALU operation will be performed? So basically first we load the value of counter into the register, load, then increment that value of registers where we have loaded the counter value, and after the increment we will again store the register value to that memory location of counter variable, right? So basically what we are doing, load R0 for register, we just writing directly to RI, okay, and for a value, since it is a memory location, we use M and variable name counter, right? Then we increment whom, so of course R0, then store at memory location M counter and value of R0. So this is the micro instruction for the counter plus plus. Similarly for the process 1 we have a micro instruction. So you always remember that we have a register which is represented by RI. I is represented the process ID or process number. So basically each process has its own register, its own register. Each process has its own register, right? So if I am writing for the micro instruction for the counter minus minus, so what will happen? So we have a first load R1 M counter, then decrement R1, then store M counter R1, right? The value of R1 will be stored in counter. These are the three micro instructions which have to execute by the process 0 and process 1. Okay, so if I execute these three instructions in an atomic manner, then there is no problem, okay, there is no data inconsistency. But what will happen if there is a context switching occurs or non-atomic execution of these instructions? So hopefully you know that what is the atomic, what is the non-atomic. Atomic is you have to execute all these three instructions at one go, so that is called atomic. Okay, so if I execute the micro instruction in atomic manner, then there is no problem, there is no race condition, there is no data inconsistency. But what will happen if there is context switching in between of these micro instructions? So the value will be changed. So let us consider three scenarios, and you can amazed that how the execution order will change the value. So I am considering case 1. So what will happen? First we will be, if I am executing the process 0 or process 0, I1 for this micro instruction, I2 for this micro instruction, and I3 for this micro instruction. Okay, so I am saying this one is the I0, I1, I2. Similarly this one is the I0, I1, I2. Okay, so what will happen? So I will put the value of R0 counter value. Okay, then I will increment value of R0 to by 1, Then I will again put the value of R0 in counter. So we'll execute the first process 0 micro instruction in an atomic manner. Then context switching occurs. Let us consider this one. Then similarly we will execute the micro instruction of process 1. So I0, I1, I2. Sorry, I1, I2. So basically I am writing that instruction name, that is load increment store. So if you want to change this instruction name, you can change it I4, I5, I6, but since these are the similar type of instruction, that's why I am taking the same name. You can change it, no issue. I1, I2, I3. Right. So what will happen? First we'll put the counter value in R1, that is load R1 M counter. Then we will decrease R1 value -1. Then we will save R1 value to the counter. Okay, so what will be the value of counter in this case? Let us check. So initially we have a counter variable is what? 5. So we'll store R0 to 5, this one executed. Then we'll increase the R0 by 1. So R0 plus 1, this 6, and then save this value to the counter. So counter equals to 6. So P0 is executed. Now next, save the value of counter to R1. R1 is 6. Then decrease the value of R1 by 1. So R1 equals to 5. Then save this value to counter. So counter equals to 5. We have executed, P1 executed. What is the value of 5 after the execution of these codes? So of course 5. Okay, so this is a case 1 where we have performed all the micro instruction in a atomic manner. Now check for case 2. I am writing the scenario. You have to give the value in chat box. What will be the value of counter? So context switching, context switching. Counter value is what? And we have a case 3. context switching, and here context switching, right? So let us check in case 2. So what will happen? R0, we have a counter value is what, 5. Then here context switching occurred and we save the value of counter again in a register 1. R1 equals to 5, right? Then R1 will decrease by 1. So R1 value is the 4. Then save the value of R1 into counter. So counter equals to R1 में क्या value है भाई, 4, right? Now increase the value of register. ठीक है, तो R0 equals to 6. We are here. Now save the value of R1 into counter. So counter equals to 4. Sorry, here it is R0. So what will happen if I save the value of R0? It is a 6. So here counter value is what, 6. Now we will execute this code. Actually I have taken two process 1 and process 2. So therefore we have taken register R1, R2. But in this case we have taken process 0, process 1. That's why there is some confusion. Okay, now first we have to execute counter value and save to the register R1. It is a 5. Then R0 5. Then we increment first R0 6. Then save the value to the counter. Counter equals to 6. Then decrement R1 by 1, 4, and save this value to the counter. So here counter value is 4. So you can see these three cases, the same shared variable and same code of execution, we have a 3 different value, right? So that is the counter 5, 4, 6 and 5, 6 and 4. So this is called inconsistent data. So why this value is inconsistent? Because there is some change of the order of execution of the code section. तो आप देखो इसमें जो कोड है वो मैंने डिफरेंट वे से एक्सिक्यूट किया, इसमें मैंने डिफरेंट वे से एक्सिक्यूट किया, डिफरेंट वे से एक्सिक्यूट किया. Therefore goal should be make sure the shared data value will be consistent. ठीक है, that's why we need a process synchronization. Since the value is different, so we can say that this is a race condition. Okay, so in detail let us see what is the race condition. If you have any doubt you can ask. So race condition. So first in during the race condition there must be some cooperating process which are competing for the same data. Okay, otherwise there is no need of race condition, or there will be no chance for the rising of race condition. Okay, so you can write it is a situation where several processes access and manipulate the same data. Okay, as I said, shared data is always reside in a critical section. For time being, we just write critical section. We will elaborate in more detail. Okay, so it is a situation where several processes access and manipulate the same data. Right. The second point under race condition, just I have seen that how the outcome depends on the order in which the access takes place. Okay, in the previous example we have seen that how a shared variable counter have a different value when we change the order of execution of micro instruction in a different manner. Okay, so you can write the outcome dependent on the order in which the access takes place. Right. Next, as I discussed, to prevent race condition, we need a synchronization. So prevent race conditions by synchronization. So basically, what is synchronization? It is a process or it is a technique which ensures only one process. This is the heart of process synchronization, that only one process can manipulate or access shared data. Only one process at a time manipulates the critical data. Here critical data means shared data. Okay, so what I am saying that, let us suppose this is my code, this is my critical section, means where the shared variable resides. Okay, so I am talking about this critical section, no more than one process should execute in, for short form I am using CS, critical section. Do not confuse with the context switching at a time. So here you can write a note, very important note, that every process has its own critical section. ठीक है? So there may be someone ask in the interview question that we have a multiple critical section exist or a single critical section shared with the different process. Okay, so we have a multiple critical section, or you can say that each process has its own critical section. Only common thing is that the shared variable which are shared among the various process, right? So you can write another notes. So race condition, till now we have seen for the uniprocessor. So what will happen in multi-core or multiple processor? So race condition in multi-core or multiprocessor. So what will be the condition? So when two or more process, I am using a new term thread. Okay, so for time being you can consider that thread is a lightweight process. Okay, it's also a type of process which is very light. Okay, we'll discuss in detail in later classes. So when two or more process or threads can access shared data and they try to change it at same time. So this is called race condition for a multi-core or multiprocessor. Same thing, that at the same time if one or more process or two or more process are competing for the shared data or manipulating, okay, then race condition will be like this. So now we will take another example to understand race condition. Let us say example 3. There is a special name of the example. So this is called producer consumer problem. Producer consumer problem. Okay, so for time being I am explaining what is the producer consumer problem. So basically in producer consumer we have two process. One is called producer process, another is called consumer process. So what is task of these two process? So the task of producer process is to produce the item or data, right? Whereas task of consumer process is to consume the items. Okay, again I am repeating, in producer consumer problem we have two processes. One is called producer process, another is called consumer process. The task of producer process is to produce the items means data items, and the task of consumer is to consume the items. Okay, since the speed of CPU is very high, so the execution of process do not match with the speed. That's why we need some memory where we can store the produced item or consume items, right? So we have a shared common buffer, okay, where producer can produce item and store that buffer, and consumer consumes the items from the buffer, right? So till now you have understood that we have two process producer and consumer, and tasks of these processes, that producer produce the item and consumer consumes the item, and these consumed or produced item will be stored in the shared buffer. Right, till now we have seen only shared data, but now here resources is also shared, that is the shared buffer. Okay, so there are some constraints. What are the constraints? So basically what we are following in stack, underflow and overflow. So these are two constraints, and other two are which we are going to explain. So for time being, those who don't know that about what is overflow, underflow. So overflow is the condition where, let us suppose I have a one bucket which capacity is 10 liter, right? Okay, so after 10 liter, if I pour the water into the bucket, overflow will be occurred. So similarly, in case of computer science, we use a overflow term if the allocated memory size is full, and if I want to put a new data or new items to that memory, allocated memory, then it is a synonyms of a bucket, means there will be a overflow. Similarly for underflow, means let us suppose I have an empty bucket and I want to take out some water from that bucket. So of course there is no water inside the bucket, this is called underflow. So in computer science, whenever these two conditions occurs, so we have always checked, means before putting a data into allocated memory, first we will check that is there chance of overflow, means we check the capacity of memory location, allocated memory location. If it's already full, we are not going to produce a new data. Similarly for the consumed process, okay, or the process which want to take data from the memory location, first we will check that is there any data available on that memory or not. So basically this is called underflow condition. So first we will check the underflow condition, then we will go for the data input, data taking data. Okay, so second constraint is, which will take from the previous example, accessing memory buffer at same time should not be allowed, because it is also a shared resources. So we cannot access memory buffer at the same time. And fourth constraint is, whatever the buffers we have, the size of buffer should be fixed, otherwise overflow condition will be not checked. Okay, so we have a four constraint: overflow, underflow, accessing memory buffer at the same time should not be allowed, and the fixed size buffer. So I'm writing, so the task of producer is to produce the item, put it into memory buffer, and again start producing items, whereas consumer process consumes the item from the memory buffer. So this is the explanation of what producer consumer problem is. So what constraints are, you can write down. In short, I am writing first is overflow, then we have a underflow, then we have a accessing memory buffer. In short, m/m is writing for memory, just like software SW, hardware HW. Memory buffer. At same time, should not be allowed. And last one is the fixed size buffer. ठीक है. So just like in previous example, we have a code for process 0 and code for process 1. Similarly, we will have a code for producer and code for consumer. Shared resources, you know, that is the buffer, and we have a global variable, that is the shared variable, that is the count. So let us see. So this is the producer code. Better to write in a new page, okay, because I have to explain it. So we have a producer code. And we have a consumer code. We have a shared variable, count. Okay. So since shared variable is global, so we will start int count equals to 0 for producer, int count. For consumer, we need not to assign the value because value of counter will be increased by the producer initially and then decreased by the consumer. So we have a function void producer. So here we have a function name void consumer. So since it will generate an item, so we'll take another variable int item p. So I am writing code and we'll learn later. So this is code for the producer and consumer. Okay, so you can see here producer can increase the value of count and consumer can decrease the value of count. Okay, so if I say we write the micro instruction for producer and consumer, so as for the previous example we can write it for counter. So load, first micro instruction is what? Load in register P for producer and memory location M count. Then increment register P, store the value of RP to the M count. So this is the micro instruction for producer. Similarly for micro instruction, load R consumer M count, decrement RC and store M count RC. So this is the micro instruction. Okay, now let us see one by one what it is. So let us suppose I have a common buffer, right? And initially we have 3 items in the buffer ABC. So this is 0, 1, 2. This is the indexing. And this is and minus 1. So initially value of count is what? The value of count is 3 because 3 data items are produced due to producer. We have you can see here the in is used. So let us consider this is the producer, this is the consumer, and out is used. So these 2 variables are local to producer and consumers. Means if I extend 3 variables in, out and count are used. Right now it's okay. So you come here, this is the while loop. Okay, so what is the meaning of this one? So we can say that special while loops, one is while count equals to n, another is while count equals to 0. So in this while loop, what basically do, if this condition is true, means we have already produced the item equivalent to the what? The allocated memory size, that is the n, because it starts from 0 to n minus 1. Okay, so it is condition of what? Overflow. So check overflow condition. If it is true, so what will happen? It is just executing the while loop forever till this condition is true. Means it will not execute the next instruction. So basically we block the execution of next instruction if overflow occurred. Similarly here we check the underflow. If there is no item in the buffer, that means count value is 0. So if it is a true, then we are not going to consume any item from the shared buffer. Okay, so basically we block the process till this condition is true. Okay, now come to the in variable. So it is only used by producer, and you can see here when there is 3 items, the value should of in is 3. So basically what it do, it is used to identify next empty slot in buffer. So if the value of in equals to 3 means we can put the next produced item into the third location of buffer, not third location, third indexed of the buffer, that is the 4th location, right? So you can see here, after producing the item, what we will do, we'll increase the value by 1, and we have taken mod n because we have the value of buffer indexing is from 0 to n minus 1. That's why we'll make sure that the value of in should not increase or not beyond to the n minus 1. That's why we have taken mod n. Similarly, we have a c count, out value or out variable. So used by, you can write it, used by consumer or used to identify that from which slot of buffer the process consume the item. So initially out equals to 0 means first we will take the value from 0 location. Okay, now third variable count. So used by both variables, both processes, global variable used by both. Then what is the used to identify the number of items present in buffer at any time. Here we have a count equals to what? 3. Right? Any problem? Okay, next we have a commonly shared. What is the commonly shared? You can see here we have a count variable is the commonly shared and buffer. Okay, till here it's okay. Now let us go to the code. Initially there is no items in a buffer, that's why count equals to 0. Now we have a producer process, so we have an integer item p. Okay, so if it is a true, means if producer wants to execute the code or produce an item, so first it will be check that there is overflow condition occur or not. If this false, means there is no overflow, then it can enters and it increases, or sorry, it put the value, generated value or generated items or data into the buffer location of in. So in is what? In represents the variable which is free to fill. Okay, after filling that value, we'll increase the in value and then increase the count value. That one item is produced and stored to the buffer. Similarly, for the consumer code, we have a global variable, it will copy the count value. Okay, so it will be item C, that means it consumes. Okay, if we want to execute, then while one should be true, else it will be false. Now it will be check the underflow condition. Now for the item C, we will take a buffer items. Okay, out 0 means what? Here we will put the A. Okay, this one will be consumed. Okay, and then out value will be increased by 1, that is we reach here, so that next consumed item will be B, and decrease the count. Since we have consumed the one item from the buffer, that's why we decrease the value of count. So this is whole about the code. Now elaborate this. Okay, so we have a 3 variables: out, count, in. A special while loop, you have seen that overflow, underflow condition checked. In is used to produce only used by the producer and used to identify the next empty slot in buffer, whereas out is used by consumer process only, used to identify that from which slot of buffer the process consumes the item. Initially out value should be 0. Then we have seen that what is the count variable, so it is a global variable used by both processes, used to identify the number of items present in the buffer. We have two things shared, that is the count variable and buffer. Now elaborate this in regarding to how the data will be produced and how data will be consumed. So you can see in producer process, count is executed by 3 different micro instruction. One is load, increment, third is store. As I earlier said, every process has its own register, has its own register, right? So here I am discussing only producer. So we have 3 data items A, B, C. Count equals to 3, in equals to 3. Now producer produces a data item D. So what will happen? So since it is a not a overflow condition, So d will be goes here. The value of count will be first in value will be changes in plus 1 divided by mod n. Okay, so it will be increases by 1, count value is increases by 1. Clear? Now we'll see the consumer side. So in consumer process, count is executed by 3 different micro instructions. Same load, decrement, store. A, B, C, D. Here count equals to 4, out equals to 0. So if we will consume this item, so what will be changes? Count value will be decreased by 1, out value will be increased by 1. Means the next data item is B, which is going to consume. So if these 6 instruction of 3 from producer, 3 from consumer, if these 6 instructions, or better to use micro instructions, are not executed properly in order, then inconsistency problem or race condition may arise. Right. So this is all about producer consumer. So on the basis of producer consumer, let us solve a problem, a very simple problem, so that some variable value and how buffer will be changed, it should be clear. Okay, so consider the following table slash buffer, then find out the value of all the variables initially. Okay, okay, so these are the given. So first let us find out the value of n. So it is a pointer to the next empty slot. In equals to what? Of course 5 is a free. Next is out variable. So pointer to the first field space, or better to use space or slot, same thing. So of course here 0. Then number of items in buffer 5, that is what count, no? Count equals to 5. Then size of buffer, n equals to 8. Okay, in the same question, find out that find out the value of all variables when producer code execute once. Further, find out the value of all the variables when producer code execute once, right? So what will happen? So let us producer produces an item f. So what will value of in? So in equals to 6 because the 6th location will be empty for the new data item. Out equals to 0 because we do not have consumed till now. Then items in buffer count will be 6. Initially it is a 5, and size of buffer will be not going to change to n equals to 8. If we execute the consumer, the value of in is what? 6. Out will be 1, count will be 5, n equals to 8. Okay, so this is all about producer consumer problem. Now let's see the another type of problem, that is called printer spooler problem. So you can take a break for the 10 minutes, or better to take a 5 minutes. We will resume classes at 11:15, right? We will start class at 11:15. All are requested. Please append your department name with your roll number. Okay, my screen is visible. Anyone?
Yes, sir.
Okay. So this is example number 4. That is the printer spooler problem. Okay. So before explaining the problem, I just writing the micro instructions which are executed for the process during print operations. Okay. So the first operation is the load RI memory location of variable in. Second micro instruction is store st RI file name. Third one is the increment RI, and last one is the store memory location of variable in value RI. So these are the 4 instructions or micro instructions which will be executed for the processes during print operations. Okay, so here SD is the, I am writing some variables name. SD is the spooler directory, SDRI. Basically SD is a SD acts as a buffer. Okay, so SDRI is the spooler directory location or ith location, spooler directory ith location, and file name is nothing. Okay, so SD basically contains set of document which will be printed by printer. Okay, so we have a two condition or two cases. Case 1, for a single process, right? So we have a printer here that basically what shared, this is the SD. Now consider process P1 wants to print file, f.doc, right? So initially we have a in variable that value is 0. Okay, so क्या होगा, it execute all the 4 micro instructions, ये वाला. तो क्या होगा initially, तो we have to load value of memory into RI. Process is 1, तो R1 value क्या है in का, initially there is no item, so in is 0. Then we have to SD0, this one store SDRI. To SD0 we have to what, store file name. File name is what, f1 dot, sorry, f.doc. Okay, then we have to increment RI. So R1 equals to what, R1 plus 1. Then store the memory location in value of R1. So what will happen? So here f.doc will be inserted and value of in will be 1. Means next 3 location is what, 1. You can write 0, 1, 2. So P1 execute spooler program successfully, and the file f.doc is queued in spooler, okay, spooler directory. So this is for the single process. Okay, in single process there is no issue, but when we go for the multiple process, so there may be a loss of there may be a chance of loss of data or overwriting of file onto the location. So let us see how it will happen. Is to multiple processes. Okay. So let us consider there is some file already residing in a spooler dictionary x.doc, y.doc, z.doc. So it is a 0, 1, 2, 3. So value of in is what? Third free location 3. All are connected to the printer. Now two process P1 and P2 wants to print a.doc, b.doc, right? So let us consider P1 first execute. If I am considering I1, I2, I3, I4, I1, I2, I3, then P2 execute I1, I2, I3. So you can see here when I2 is executed, this one, okay, to at third location we will write the a.doc. Okay, when P2 execute the I1, so it get the free slot location is what? 3, because P1 is not completed yet. That's why the value of free slot will not increased. Okay, so what P2 will do at the time of micro instruction I2, right? It will also got the same free location, in value is 3, so it will be overwrite b.doc. So you can see here we have overwrite, okay, and now P1 execute I4 and P2 execute I4. So this will gives the value of I in equals to 4. Next free location is 4. But what we have done, we have overwrite due to the non-executing atomic instruction. Okay, now please mute yourself and let me check. Okay, so here you can see due to this we suffered a loss of data. The event occurred due to non-synchronization of P1 and P2. यहाँ पे क्या हुआ, यहाँ सिंक्रोनाइजेशन तो हुआ नहीं, P1 first P1 have to completed then P2. Okay, so in between they change their execution of micro instruction, and they got a wrong value of the free slot. Basically P2 have got a wrong value of free slot. That's why it write on the third free locations. Okay, so in the coming class, not right now, in the very later classes, we will see what is the solution. So basically we will use a two type of solution. One is called semaphore, another is called mutex. So basically semaphore is the operating system supported protocol and mutex is the simple lock. Okay, that is lock. Okay, so these are the two things, these are the two supports by which we can synchronize the process, but right now you can forget it. Okay, just remember the terms semaphore and mutex. So I will first take the attendance and then we will resume the classes. Okay, from the what are the different sections and elements of program. So basically in a program we have a multiple sections. Program means codes. Okay, so basically we have a entry section, we have a critical section, we have a exit section, we have a remainder section. Okay, so we'll see one by one in detail. First I will took the attendance. Okay, is there any rule for which we can identify the roll number from the CSC, EC and DESA? If 001 is the CSI, right?
No, so we have 4 zeros in CSE, 101 in EC.
Okay, first I will took the I will take the CSC, then I will ask what is the nomenclature.
Okay, sir.
Okay, what about EC? Anyone?
Sir, 22101.
221.
01.
Okay, okay. Aditya Raj, what is your roll number? Anirudh, Pushparaj, Rajdeep, Vajrika.
Sir, Pushparaj, roll number CSE 42.
42. Okay. DSI 18. Okay.
Sir, Rajdeep, CSC 45.
CSC 45.
Yes.
ओके अमित कुमार 2210200405 इसी ही हो क्या? Okay, I will repeat the roll number of absentees. Please correct. CSC 7 10 6 7 10 18 24 26 31 49 55 61. Okay, इसी
So
one
these are for absentees or presentees?
absentees.
Oh,
इसी 1 3 4 5 6 8 15 20 30 31 34 35 36 39 40 42 44 47 56 57 58. Data science 1 10 12 13 16 17 19 27 28 54 58 60.
58 present, sir.
58.
Yes, sir. Yes, sir.
Okay.
Vajral Akhilesh.
Okay.
Thank you, sir.
Okay, we'll resume the class. Is there anyone left? Okay. Okay, so let us come to the next section, that is the different sections and elements of program. So we have a entry section, then critical section. We'll elaborate one by one. Then we have a exit section, then remainder section. One or true, whatever you want, you can write it. Either you can write while true or you can write here while one. No difference. Okay, both are the same, do while and while. Okay, so let us see what is the entry section. So basically it controls the entry into critical section. For example, there is a multiple process, okay, who is competing for the critical section. So basically entry section has some condition or some logics okay, by which it controls the process entering into the critical section, right? A critical section, so we know very well it is a section of code where the shared resources or variables are shared. Section of code where the shared resources or variables, shared variables are shared, right? Now what about exit section? So basically it handles the entry of other, for example let us suppose we have a three process, right? P1, P2, P3. P1 is executing the critical section, and now after the completion of execution, P1 leaves the critical section. Then there must be some condition to P2 or P3 to enter the critical section. What I want to say that, okay, let us suppose we have two process P1, P2. So whenever P1 entering its critical section, it has okay, Anirudh, wait. It has some logics so that the other process P2 will be not enters into the critical section. Okay, when it finishes its execution into the critical section, then it have to enable, okay, so that the other process can enters. Okay, so basically exit section handles entry of other processes that are waiting in the entry section for critical section. Another thing, exit section also handles the removal of the task which have already completed their critical section. Handles removal of process that finished its execution. What about remainder section? So apart from entry section, critical section, exit section, whatever the code or part of code, okay, is known as remainder section. So all other parts of which is not in critical entry exit section are known as remainder section. Okay, yes, Anirudh. Okay. Clear? So we have a different section of programs: entry section, critical section, exit section, remainder section. So critical section, you know, it is a section of code where the shared resources or variables are shared. Now the next is, what is a critical section problem, which basically we are our main focus, which we are dealing into the process synchronization. So critical section problem. So basically critical section problem is a how we can design a protocol please listen carefully, how we design a protocol that process can cooperate. Okay, so the protocol ensure that when one process is executing its critical section, no other process is allowed to execute its critical section, right? So the protocol ensure again the process which use protocol, the output will not depends on the order in which they execute. Till now we have seen many examples that whenever we change the order of execution, the output will be changed, that is the race condition. So we have to design a protocol that mainly two tasks to perform. Okay, protocol for whom? Protocol for cooperating process. The first task is it makes sure that no two process can access at the same time of critical section. Another task is it's ensure that the output will not depends on the order of execution of instructions. Okay, so this is the critical section problem. So you can write critical section problem is to design a protocol that process can cooperate. The protocol ensures that no two process, no two or more process can execute their critical section at any time. Okay, it also ensures that the process which use protocol the output will not depends on the order in which they execute, right? I hope the problem is clear. We have to define a design a protocol which has two tasks. First one is that no two or more process can access or manipulate the shared data at the same time in their critical section. Another task is to make sure that the output will be not depends on the order of execution of instructions, right? So this is all about the problem. Now let's come on the requirements for the solution of critical section. Okay, what are the requirements to design such protocols? Requirements for solution of critical section. So before starting this, we have a three term which we should know. Okay, so first one is the mutual exclusion. Mutual exclusion, in short it is called ME. Okay, so what is the ME? So basically mutual exclusion says that no two processes are present simultaneously inside the critical section at any time. So basically it represents the safety, so that overwrite on data or manipulation of data by two different programs is not occurred. Okay, so what is the mutual exclusion? So basically it's ensured that no two process simultaneously execute their critical section, okay, at any time. Why it is a constraint? Because due to this we can ensure that the data value will be not manipulated in the order of execution. Okay, so it is called safety. So mutual exclusion, I hope clear. That is the protocol first task, that it's ensure that when one process is executing its critical section, no other process is allowed to execute its critical section. So this is all about mutual exclusion. The same mutual exclusion can also be used in deadlocks. Okay, whenever we are going to study about the deadlock, there is a one condition for deadlock, that is the mutual exclusion. So in that chapter, basically we are talking about the mutual exclusion in terms of resources. Just like in example you have seen that there is a railway track, okay, and two trains are coming. So here the resources are shared. So is the railway track is mutually exclusive? No, because both the trains used at the same time. So if mutual exclusion is not, so there is chances of deadlock. Okay, for time being you can remember it. So next term is the progress. As term suggests, progress means what? Any work or any task is going on or not. Okay, so progress basically says that if no process is executing its critical section, means critical section is right now empty, okay, then the section of process for the critical section cannot be postponed indefinitely. Okay, so if there is no process inside the critical section, if I want to elaborate in a simple words, if any other process wants to critical section, then the critical section is allowed to execute by that process. Okay, in other terms you can say that a process executing outsides of its critical section, just like in code section you have seen, outside means what? This side. Okay, a process, let us suppose P1 executing its critical section, and now it's comes into exit section, right? So it do not block the any process who wants to enter its critical section. So we'll see in the coming examples how the process which are exiting has postponed the execution of critical section by the other willingness processes. Okay, right? The third term is comes bounded waiting. Right now we have seen what is the mutual exclusion, what is a progress. So basically mutual exclusion used for the safety purpose, so that data will be not overwritten. Progress is basically represents the prevention of deadlock. Okay, prevention of deadlock. Third one is the bounded waiting. So what is bounded waiting? So if you break the word bounded, means we bound or we limit something. Whom? The waiting means we limit the waiting of any process. So basically bounded waiting is no process should have to wait forever to enter its critical section. There should be a bound on getting chance to enter into critical section, right? So in other words, you can say that there is a limit to how many other processes are able to access their critical section before the requested process request is granted, right? So what will be the disadvantage if we are not following the bounded waiting? So if any solution is not following bounded waiting, then there is a possibility of what? Starvation, because their low priority process is waiting for a indefinitely time span. That's why solution, whatever we are going to give the requirements for the solution, must be a bounded waiting. So basically 4 types of requirements for any solution of critical section problem. First, it should follow the mutual exclusion, it should follow the progress, it should follow the bounded waiting. Okay, so we have a various types of software hardware solution. So basically we will check software solution for these critical section requirements and hardware also. Okay, so for example, there is a solution called software solution called algorithm 1, that is the Baker's algorithm. So where we can see that mutual exclusion is achieved but progress and bounded progress do not achieved, bounded waiting is achieved. Okay, similarly in the algorithm 2 solution, that is called flag variable solution, to where we can see that only mutual exclusion is achieved, progress and bounded waiting have not achieved. Okay, the third is the software solution is called Peterson solution, which basically use the two first and second algorithm. Okay, where we can see that all the 3 are achieved. Okay, so this is all about, we'll going to study about the next classes. This is the basics. Right now we are just completed the basics of the synchronization, process synchronization, or you can say that the introductory terms or basic requirements to understand how we can design protocols, okay, to make sure process should be synchronized. So in coming classes we will see in details. So next Monday there is a holiday, so we'll try to schedule a class on Saturday. Okay, if anyone wants to go to home, to please join from there. Okay, anyone wants to say something, you can say, else we will stop the meeting, or chat box you can message also. ओके, रोल नंबर किसी का छूट गया, किसका छूटा है? 7 CSC।
यस सर, 7 सी।
एक मिनट, और किसी का छूटा है तो एक बार फिर से रुको, हम चैट ही बड़ा कर लेते हैं।
रोल नंबर 1 CSC।
एक मिनट 7 इज प्रेजेंट।
CSC रोल नंबर 1।
CSC 1 प्रेजेंट हो, और 7 प्रेजेंट। कितना बार मैसेज करते हो जी 7? और कोई हो जो छुट्टे हो? 39 CSC, 39 इज ऑलरेडी प्रेजेंट, 31 CSC। ओके, ठीक है, और कोई हो तो बता दो रोल नंबर, अदरवाइज यू कैन लीव। थैंक यू।
Thank
थैंक यू सर। थैंक यू सर। सर थैंक यू
sir. 31 DSI.
31 DSI,
Sir, 48 DS.
और तुम दोनों तो प्रेजेंट ही हो।
सर 22 DSAI।
तुम लोग सुने नहीं थे क्या जिसका बोले थे? हम एक बार फिर से रिपीट कर देना। CSC रोल नंबर ऑफ एब्सेंटीज आर 10, 18, 24, 26, 49, 55, 61।
62 DSAI।
DSI 1, 10, 12, 13, 16, 17, 19, 27, 28, 54, 60। क्लियर? और इसी 1, 3, 4, 6, 8, 15, 20, 30, 31, 34, 35, 36, 39, 40, 42, 44, 47, 56, 57, 58। DSI 8 प्रेजेंट हो भाई। ठीक है, और किसी का अगर छूट गया होगा तो वो मेल कर देना। एक सेकेंड। DSI सुनाई नहीं देता है क्या तुम लोगों को? फिर से हम रिपीट कर रहे हैं। रोल नंबर ऑफ एब्सेंटीज आर DSI 1, 10, 12, 13, 16, 17, 19, 27, 28, 54, 60।
DSAI।
हाँ, एक बार फिर से बोलो। 61 प्रेजेंट है। जो एब्सेंट है हम उसी का बोल रहे हैं। CSC 57। ठीक है, चलो, थैंक यू।